doing linear transformations. Today also we are going to continue with the same, that is the linear transformations, and a few problems regarding linear transformation. Okay, like how to judge whether it is a linear transformation or not, problems like that. Okay. Okay, let's begin without wasting further time. So as you are aware that yesterday itself I actually it's yesterday itself I actually defined the two important properties uh, according to which you can define a linear transformation, right? So yesterday itself we did what is transformation. We did that linear transformation is a mapping between two vector space. Okay, it is a mapping between two vector space. So after having learned vector spaces, subspaces, dimensions, and all those things, now we have and come to a point where we are understanding the functions, like functions between the two vector spaces. Okay, or in general mapping between two vector spaces. Okay, and a few mappings we have already seen that they are linear transformation. What are the conditions that are required for linear transformation? The first one is that if you are saying that there is a linear transformation defined from u to v, then remember that tu1 plus tu2 should be equals to tu1 plus u2. Okay, and since we are from physics, we can use the word interchangeably. That is, instead of linear transformation, you can say all these things as linear operators also. Okay, because in physics that is more used, as if understand that even in mathematics also we use the word operators, but mostly in physics we precisely have understanding with regards to the word linear operators. Okay, so whether you say linear transformation or linear operators, they are one and the same thing. So what are the properties? The property number one is that if you take the I mean if you want to take the map of u1 plus u2, then it's equal to this is point number one. And secondly, if you take an alpha from field f, and if you want to take t u, then it comes out to be tu. According to these two properties, if 0 is an identity element in u, then t of u is always equals to 0. T of 0 is always equal to 0. Please do remember this. Okay, and second and other property is that if you want to find t of minus u, it is equals to minus of tu. So all these properties in general, mostly these two properties are important. These two follow from this only. And another way to express that whether your operator is a linear operator or not is to write this kind of thing. And if this happens to be this, we'll say that T is a linear operator, okay, or linear transformation. Okay. So yesterday we did a quite amount of question. Today also we are going to continue with the same. That is, we are going to see the questions, and we are going to see what makes a linear operator. Okay, what makes a linear operator. So let us take another question from today, and I'll give you 2 minutes to think on the question. If you're not able to think, then I'll go on doing this. Okay, so let us start. Okay, it says that for a fixed vector, a1, a2, a3 belongs to R cube, we want to define a mapping. Let us define a mapping. Let us define a mapping that is T from R cube to R by T x1, comma x2, comma x3 equals to a1 x1 plus a2 x2 plus a3 x3. So this is how I have defined my mapping. We have to show, what do you understand by this? If you remember, this represents the scalar product. This represents the scalar product between a n, you can say, or you can say dot product if you remember, dot product between x1, x2 and x3 and a1, a2, a3. So we want to prove that this is a linear transformation. That is the dot product is the, we have to show that this is the linear transformation. Okay, we have to show that this is the linear transformation. Okay, how to go about it? So I told you yesterday, so in order to see a linear transformation, what all we need to do first is, let us take two coordinates. Let us take two points. Let's say x is equals to x1, x2 and x3, x3, and y is equal to, let's say, y1, y2 and y3. This is how you define your x and y. Okay, now let us define the sum of both. So I'm going to define t of x plus y, which is equals to t of x1 plus y1 comma x2 plus y2 comma x3 plus y3. And what this transformation is going to do, since a is a fixed vector, so if you supply this, it multiplies a1 to the first coordinate. So I'll multiply a1 to the first coordinate, a2 to the second coordinate, which is x2 plus y2, and a3 to the third coordinate, which is x3 plus y3. Okay, so this is how you define. Now, if you like expand this up, what you will get a1 x1 plus a2 x2 plus a3 x3, and another one bracket you will get a1 y1 plus a2 y2 plus a3 y3. Okay, this is 1 and this is 2. Just remember, what is this? This is nothing but it is tx, and this is nothing but this is ty. So we can say that this holds the first property regarding linear transformation. Now let us take any alpha belongs to R, the scalar quantity. Let us take alpha belongs to R and try to find t alpha x. So what would be t alpha x? It would be simply t alpha x1 comma alpha x2 comma alpha x3, and eventually you can write this as a times alpha x1 plus a1 times alpha x1, a2 times alpha x2 plus a3 times alpha x3. And if you take alpha common out, you're getting a1 x1 plus a2 x2 plus a3 x3, and therefore you can say that this is equals to t times alpha times t. So if you can say that this transformation, which is represented by the dot product, is linear. It is a linear transformation. It is indeed a linear transformation. I hope it is clear. Now let us find another operator and try to see whether this is a linear operator or not. So actually I'm interchangeably using operator and transformation, so don't get confused. Okay, you can use both of them. Okay, you can use both of them. So this is your question number 2. We have to show that map given by RQ to RQ defined by let's say this is my thing, tx1 x1 x2 x3 is equals to x1 plus x2, oh sorry, minus comma 2x1 okay. So we have to prove that whether this is a linear transformation or not. Okay, we have to prove that whether this is a linear transformation or whether this kind of operator with this kind of transformation, what is transformation? Understand, see, transformation is you supply me 3 tuples, that is x1 x2 x3. The first one in the on the range side, you can say it will transform into x1 plus x2 minus x3. So it's no longer going to be x1, it's going to be this, and it's going to be this, and it's going to be this. So obviously this represents certain transformation from R cube to R cube. Okay, so let us try to find whether this is a linear transformation or not. So again, I'll take two things, x and y. Let us take x and y. Both of them I have taken, and I want to see whether t of x plus y is equals to tx plus ty. Right? This is what I want to see. So this is how it is going to be. So I'm going to write this as x1 plus y1 then I'm going to write it as x2 plus y2, and then I'm going to write it as x3 plus y3. And it's quite obvious that the first one would be x1 plus y1, and then you will have this x2 plus y2, and then you will have minus of x3 minus of y3, comma, this would be equals to 2 times x1 plus 2 times y1 minus x2 minus y2, and third one would be, I think this would be x2 plus y2, and then you will have 2x3 plus y3. Okay, this is how I can write. And the same thing can be written as, I think it is quite easy to see that this would be x1 plus x2 minus x3, comma, 2x1 minus x2, comma, x2 plus 2x3, and I can add this up and write it, add it with x1 y1 plus y2 minus y3, comma, 2y1 minus y2, and the last coordinate will be, I think, y2 plus 2y3. So this is how I can write, and you can understand that this is equals to tx plus y is equals to tx plus ty. And similarly, I would say that similarly you can prove that t alpha x1 comma alpha x2 comma alpha x3, so where alpha is belongs to r, it will be equals to what? It will be equals to alpha x1 plus alpha x2 minus alpha x3 to alpha x1, what was the second one, minus alpha x2 comma alpha x2 plus 2 alpha x3, and then you can take this alpha common out and this will become tx. So eventually you know that this is t times alpha x, and t times alpha, t of alpha x, sorry, not t times, t of alpha x is equals to alpha tx. So clearly I can say that t is a linear transformation. So t is a linear transformation. I hope it is clear. Okay, so let us take another. I'll take today questions only so that you are aware with this thing. Okay. Uh, a few technical things will also crop up in between, but don't worry about that. Okay, somehow I'll take care of that. So we've already come across, if you are aware that we've already come across a linear vector space which is given by Pn. So Pn represents what? Pn represents the set of all polynomials. It represents what? It represents the set of all polynomials uh, whose of degree at most n, of degree at most n. So we have come across this set of all polynomials of degree at most n. Okay, and let us let us take some function. Let us take some polynomial from this Pn given by alpha naught plus alpha 1 x1 plus alpha 2. I'll take x square better. Okay. So dash 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 alpha. So what I have taken from this set of polynomials of at most degree n, I have chosen this particular polynomial, and I'm defining an operator which is df, which is nothing but the derivative. We want to show that. However, I can show that in general also, but let us take an example and try doing that. So we have to show that this transformation, that is d from Pn to Pn, and what is this? Understand, this is nothing but this is the differential operator. Okay, the differential operator is a linear transformation. Let us show that this operator d from Pn to Pn is a linear transformation. This is a linear transformation. Okay. Okay. So I have taken an example to demonstrate that. In general, always remember that the differential operator is a linear transformation. It is a linear transformation, so it is a linear operator. And specifically, when you're going to study quantum mechanics, your linear momentum, okay, in x direction, let's say minus iota h squared del by del x. This is also a linear operator. In three dimension, this is also a linear operator, because this derivative d by dx happens to be a linear operator. Okay, so. Okay, so let us try to do this. Okay, let us try to do this. So let me take two of the examples, two functions, and then we'll be able to do it. Okay, so let me take two. So, so let me take f. Fx is given to you. I think alpha naught plus. Oh, I should have chosen some different thing. I think. Cool, but let it be. I've chosen alpha now. So let us make it. Okay, let it be now. Alpha x. Okay, this is one. And let us take gx to be equals to beta naught plus beta 1x plus beta 2x square and beta n and xn. I know that what is my df? My df would be simply, so I'll do one thing. I'll go for a general proof. Now, I've done it two times using this. Like I have separately proven them. Once I have proven the addition, and another time I have proven the scalar multiplication. Now, let us not complicate things. Directly, let me write in this fashion. Let us say, I should have taken some other thing now. Okay, so let me try to do. Uh, Let me try to write what is AF plus BG. So my AF plus BG would be A alpha naught plus A alpha 1 times x plus A alpha 2 times x square A alpha n x raised to power n. And if I want to write what would be BG, so BG would be equals to B beta naught plus B beta 1 x plus B beta 2 x square and b beta n xn. Okay, now let us try to write the operator. Let us see that what does this operator does. So I told you this operator would do what? This operator would uh, like you like according to this definition, it's going to reduce. It is going to differentiate it. Okay, so what I'm going to what I will be left with simply a alpha 1 plus 2a alpha 2 x, and at the end I'll get n a alpha n x raised to power n minus 1, and then you will have this plus b beta 1 plus 2b beta 2 x dash 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 n b beta x raised to power n minus 1. Okay, so this is how it is going to be. So d af plus bg would be equals to what? It will be equals to writing a d, simply this is what this particular, if I take a common out, this is simply writing a times df plus b times dg. So effectively I can say that this particular d, that is the linear operator, sorry, there's the differential operator, this particular differential operator is a linear transformation. It is a linear transformation. I hope it is clear. Uh, uh, okay, now let us take question number 4. Okay, so as I told you, today it's just about questions so that you'll be able to understand, and this is like very useful also. See, I told you many a times that even in see quantum mechanics is the the postulate says what, that every observable, like you see in classical mechanics. So if you want to draw a correspondence between classical and quantum, so every observable in the classical mechanics has has an operator form in quantum mechanics. And what are those operators? Those are linear Hermitian operators. So understand all these things, happen to draw a very good happen to draw an underlying structure of the quantum mechanics. Okay, so this linear algebra is the heart of quantum mechanics. If you understand this particular thing, and time and again I've told you that probably everybody lacks an insight, like physical insight in quantum mechanics. Like for example, for me also, for anybody like who's into teaching and started teaching, nobody can claim that I know quantum mechanics to the level extent. Okay, nobody has got that kind of physical insight. Uh, Probably people like VK Balakrishnan may get after getting so much of experience after teaching. Okay, but we people don't have that kind of physical insight. So, what is a way ahead to clear the exam or just to get just to get into some institute, some PhD entrance? So, the way is that somehow you relate yourself with the mathematics part of it, and once you are done with that mathematics part of it, you're going to uh, you're going to solve the problems, and then things are going to come eventually to your head also. But initially, my pedagogy would be to like do more mathematics in this quantum mechanics course, so that you're aware with at least solving stuff. Okay, so our strategy is to do quantum mechanics, then to understand what it is going to see. All these things, again, I'm saying the physical insight is like, for example, you want to see a physical insight in quantum mechanics, then the spectroscopy and all those things, like for example, superconductivity, all those are what? They are physical realizations, right? Which have got quantum mechanical answers. For example, even magnetism, the field which I have worked. So magnetism cannot be explained beyond, like it is what completely a quantum mechanical phenomenon. But it is governed by spins. The spins has got no classical analog. Okay, but you see, uh, whatever we do on mathematics framework, we eventually see that happening in front of our eyes. So this is how the postulatory approach is correct, like in quantum mechanics. We take some postulate, we try to work out with them, and after having worked out with them and seeing the same things happening in the experimental realization, gives us a answer that okay, whatever you've done, whatever framework you've developed, it's quite correct. Okay, recently there was a paper, I think it's still there on archive. It says that the conceptualization of Hilbert space is unphysical, less physically realizable at some point. I don't know, but the authors say that way. It's just on archive. I think a few days back I saw that paper. So the point is this: it's all evolving. Okay, it's all evolving. So okay, so let us do. I think another question, and then I'll develop into some. I'll go into some other site. Okay, so understand that this particular scenario that I told you just now, that if I have this two, I had taken two functions like f and g and proven that alpha and beta g or whatsoever it was af and beta g, and I took this t times alpha f and beta times g, and I had proven that alpha t f plus beta tg. So this is how I can say that my T is a linear transformation. The same thing can be extended for a more general scenario. For a more general scenario, that is, I can do this also. What should I write? I can write this also. Okay. If I want to say that it is a linear transformation, then I can go on writing this. I'm saying that T is a linear transformation, then it implies this, where alpha i's are some entries from field F and ui's are vector from the vector space U. Okay, so this is equals to T u1, and then you have this alpha 2 tu2, and then so on and so forth, alpha n tun. Okay, so this is how you can extend the definition that you've been doing. Okay, so it has been defined like that. Bharat says that is there any reason for why only linear operators for physical observations, or it has been defined like that? As much as I understand, it has been defined like that. Look, this is a postulate that they have taken, and postulate after having complete rigorous experimentation that had led to this kind of postulatory approach. So this is what we see in books also, that this is a postulate. Postulate means what? We have taken this and we see this happening. So whatever things we have calculated from there, we see the things happening there. Okay, so therefore linear operators, and specifically Hermitian operators, everybody understand that whatsoever the quantification is is there. Let's say if I say that this is ax is equal to lambda x, so whatever quantification is there is it's realized, or you can say that this quantification is manifested in form over the eigenvalue. Okay, so for example, if I say that h ket psi n gives me en psi n. So this particular thing should be some real entity, right? So therefore Hermitian operators, uh, so that is what I feel. Although I need to get back into literature and find more explanatory answers to that, and I may find a few of them. But let us wait for that particular thing to happen. Let us now come back to the this particular thing. Okay. Now we want to see. Let us do simple question first, and okay. Okay. Now there is another, you can say theorem, or you can say a statement I'm writing. Okay. So let V be a vector space. Let V be a vector space, and let T be defined from R, that is a set of real numbers, to a vector space V. And understand this set of real numbers also form a vector space. Okay. Set of real numbers form a vector space. To V be a linear transformation. So I'm claiming that this T is a linear transformation. Then there exists V belongs to V, that is a vector V belongs to capital V, such that T of alpha is equals to alpha V. So what it is doing, it is saying that I'm taking an input alpha from R, and there always exists some V belongs to vector V such that T alpha would be equals to alpha V for all alpha belongs to R. So for all alpha belongs to R. See, understand just a little bit of it. It's not that you completely understand it. Okay, so just I'm trying to develop some, you can say, commonality of, okay, sorry, some understanding to whatever I have written. Let me just help you with this. Where is the pen? Okay, so okay, so this is what it is. Not answer, just an idea. Okay, just an idea. See, what do you think the basis of R would be? So basis of R would be simply singleton one, right? You want to generate any element of R, you want to generate any element of R, just use one. So for example, whenever I was telling what is the basis for R square, the basis for R square was 1 comma 0 and 0 comma 1. If I want to write what is the basis of R, so one of the bases of R can be one, simply one, singleton one. Is that clear? So if I want to take this linear transformation of T of 1, what am I going to get? I'm going to get this V. Is that clear? Okay. Okay. So I'm claiming that uh, if I take the image of 1, it would be some vector V, right? It would be some vector V. See, this is the linear transformation. T, a linear transformation defined from set of real numbers to V. V is a vector space. So one of the understanding is, it says that a basis of R would be 1, singleton 1. Okay. You generate any real number. You can generate any real number by scalar product with 1. Is that clear? So I'm just taking an image. An image would correspond to some element in V, right? This is how it is. Image would correspond to some element in V. Now, for any alpha, if you want to take image, T alpha. So what I can say, it is nothing but it is equal to T alpha into 1, and which it will be equals to alpha into T1. And what is T1? T1 would be some vector V. So always remember, so there would be some vector V always, such that if I take this T alpha, you will get alpha V here. Okay, so this, just understand, this is one of the just properties. Okay, one of the properties. So if V be the vector space and T be defined from R to V be a linear transformation, then there exists some vector V belongs to capital V such that T alpha is equal to alpha V. Now let us come back to what I was discussing, and let us do a question first. Okay, let us do a question first and understand. Okay, so let us do a question. So question says that uh, uh, what should I write? Okay, simple question again. let us define, let's say we define a linear operator from r square to r square. So it is a linear operator. So I have declared that this is linear. Linear operator means this is a linear transformation, point number one, such that t 0, 1 comma 0 is equal to 0 comma 1, and t of 0 comma 5 is equal to 1 comma 0. Now I want to find what is 3 t of 3 comma 5, or okay, and one more question, just give me the answer to that, whether you think that t1f is equal to t5, sorry, 3 t35 is equal to t53. Okay, so what do you think? I'm giving you a minute to think about it. I think this can be commented, like you can put this in comments. You just have to give me the ordered pair. What do you think 3 comma 5 linear transformation t, so t of 3 comma 5, what it is going to be? See, let me help you. Okay, so what do you understand out of this? So, for example, from here I can say that. So, from here I can say that 1 comma 0 and 0 comma 5 are basis for r square. Are a basis. Okay, I'm not saying that they are standard basis. I'm saying they're basis of r square, right? But so you can. I told you now that 0 comma 1, sorry, 1 comma 0 and 0 comma 1 are called as a standard basis. They are called as a standard basis. But in general, from this problem, you can say that you're able to express the coordinates in terms of the images of 1 comma 0 and 0 comma 5. Okay, so I can write that these are the basis for r square, and in order to check, you can check it quite easily, that their dot product is 0, so they're orthogonal to each other, so they are linearly independent to each other. Okay, and if you don't want to check dot product, as of now I've not given you that definition, then you can check for the linear independence by making their linear combinations and equating them to 0. Okay, that is quite easy to see. So both of them are basis for r square, isn't it? If I want to write t3 comma 5, I can write t3 comma 5 as simply 3 times 1 comma 0 plus 1 times 0 comma 5. Okay, is that clear? And this I can write that t3 comma 5 is nothing but it is equal to 3 times what is 1 comma 0. Just remember that sorry, what it has happened, I think. Okay, not t, sorry, what I can, not t, uh, 3 comma 5 can be written as 3 times 1 comma 0 and 1 times 0 comma 5, right? This is how I can write my 3 comma 5. So I can express my vector 3 comma 5 as a linear combination of 1 comma 0 and 0 comma 5. Having said that 1 comma 0 and 0 comma 5 forms a uh, forms a what I can say 1 comma 0 and 0 comma 5 forms a basis set for the R square. So 3 comma 5 can be written this way. So I'll apply now transformation. Transformation implies t times, since it is a linear transformation, since I've been given that t is a linear operator, so t 3 1 comma 0 would correspond to what? It will correspond to 3 times t 1 comma 0, right? And this is how I'm going to write, and this it's simply 1, and this is t 0 comma 5. See, what is t1 comma 0? T1 comma 0 is simply 0 comma 1, and t0 comma 5, it is simply equals to 1 comma 0. And so from here you can write it as 1 comma 3, right? Indeed, so Bharat is right. So it is simply 1 comma 3. Okay, so t3 comma 5 is simply 1 comma 3. And similarly, if I want to write 5 comma 3, so how can I write 5 comma 3? So 5 comma 3 can be written as 5 times 1 comma 0 plus what should I write? 3 by 5 times of 0 comma 5, right? This is how I can write. And if I take a transformation both sides, this is 5 t comma 0 t 1 comma 0, and then you have this 3 by 5 t of 0 comma 5. Okay, and from here it's quite easy to see that this is simply what is t1 comma 0? This is 0 comma 1, and then plus 3 by 5 t of 0 comma 5, that is 1 comma 0. Okay, so you're going to get 3 by 5 comma 5. Clearly you can see that t3 comma 5 is 1 comma 3, and it is not equal to t5 comma 3. Okay, I hope that you've got this point. Now I'll do a few more questions, then we'll move to a very important concept of rank and nullity. Then we'll move to a concept called as rank and nullity. Okay, now let us take another question about linear transformation only. Okay, see, I'm defining two functions now. Define a linear, or not linear, I'm not saying linear right now. Okay, let us first find whether they are linear or not. Let us define t from r square to r square, and s from r square to r square, r square to r square. Okay. Okay, and see, now I'm going to write it in matrix form. Okay, so that I'm going to declare a column vector here, and is equals to 2 times okay. Now let us see whether they are forming whether T and S are linear transformations or not. Let us see whether T and S are linear transformations or not. So for observing that they are linear transformations or not, what I am going to do, I am going to write this. Okay, I think the battery is okay. So I'm going to take this x as x1, x2, and y as y1, y2, and then I'm going to test it for tx plus y, which is simply t of x1 plus y1, and then you will have this x2 plus y2 here. Okay, and this would be equals to what? This will be equals to 2 times x1 plus y1, and then you will have this 2 times x2 plus y2, and then you have a 0. Okay, what it is going to do, just take this x and y, and sorry, this is not 2, this is y. Okay, so the y coordinate will be added as it is, and the x coordinate is multiplied by 2 and then added, and here you have a 0, so I have written a 0 here, and eventually it equates to x1 to x1 plus I think x2, right? And then you have a 0 here, and then added to it is 2y1 plus y2, and then you have a 0 here. So clearly, yes, T forms a linear transformation. T forms oh no, another property needs to be checked. but right, I can say that my tx plus y is simply tx plus ty. So this forms a linear transformation, right? So let us take t gamma, you take t alpha x, so it is equals to t alpha x1 alpha x2, and which is equivalent to writing 2 times alpha x1 plus alpha x2, and then you have a 0 here, you take alpha common, you'll get 2x1 plus x2, and then you have a 0, so you'll get alpha tx. So I can say that yes, t indeed forms a linear transformation. Just check it for s. Do you think that s forms a linear transformation? I'm giving you a minute. By that time I'll bring the charger because the laptop is off. So here is the definition. Just try to check it. Okay, so let us check whether S forms a linear transformation or not. So in order to check that whether S forms a linear transformation or not, so again I have taken these two things only. So S x1 uh, x2 plus y1 and y2. So what it will yield me? It will yield me. Uh, the first bracket was I think x1 plus x plus y, right? So I think okay. You do one thing. You do one thing. It's better to get into this mess than just so. I'll claim reverse. Okay, so it will be easy to do it this way. Okay, so at times you can do this way also. Okay, where is the eraser? Okay, so what I'll do, instead of selecting this x and y, because it will be very difficult to it will be very difficult to uh, get them back. So I know that this is not a linear transformation, so I'm going to negate it. Okay, so I'll take two special cases. So if it is a linear transformation, then it should preserve this vector addition, right? So if I'm saying that s of 1 comma 0, it would be equals to what? It will be 1 plus 0 into 1 into 0. So it should be equal to what? It should be equal to, I think, 1 comma 0. And if I want to write s of 0 comma 1, then it should be equal to again 1 and 0. Okay, but if you think that I'm adding these two up, that is 1 0 plus 0 1, this particular thing should be equal to what? It should be equal to s of 1 1. And what would be s of 1 1? It would be 2 comma 0. But if s is a linear transformation, if f is s is a linear transformation, it implies what? If s is a linear transformation, then s of this should be equal to s1 comma 0 plus s of 0 comma 1, which is eventually equals to what? Right? Oh, not this. This should be 1, right? Okay, 1. Then it should be equal to what? It should be equal to 2 comma 0, which is not equal to 2 comma 1. So therefore, we arrive at a contradiction. So I have contradicted it. So we arrive at a contradiction. So therefore, we can say that S is not a linear transformation. Okay, S is not a linear transformations. I hope it is clear till now. Okay, so s of 1 comma 1 is 2 comma 1, right? Sorry. So s of 1 comma 1 is 2 comma 1. So therefore, it's not a linear transformation. Okay. So having said all these things, now let us understand a few vector spaces. Let us discuss a few vector spaces, and these are very precisely some important vector spaces that you're going to see quite often in your linear algebra course. That is rank and nullity. Rank is space and null space. Okay. I have not taught you quotient space throughout because I think that is more related to physics, mathematics. But if time permits, I'll make some lecture and put it as a recorded ones on YouTube, so that if you feel that if you want to learn them, like quotient spaces, then you can go through them. Okay. So, one of the important theorems before beginning this is, please remember that if let E1, E2, E3 dash 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 En be a basis of U, and V1, V2 dash 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 Vn be vectors in N, be any N vectors in V, then there is only a unique image. Then there is, I will write not unique, there is only one, there is only one, there is um, you can say one and only one, there is one and only one linear transformation. That is, there is a unique transformation which relates what? Which relates basis to the vectors, which relates the basis to the vector. Okay, so always remember, so if you have a basis in U and there are n vectors here, then there is only one and only one transformation that relates basis to the vectors. So just by an example, I'm going to make you understand this. Let us take what should I say? Let us take an example. Okay, let us take an example and understand what I want to convey. So let us take standard basis for R cube. So let's say 1 comma 0 comma 0, 0 comma 0, 0 comma 1 comma 0, 0 0 1. Let us take these standard bases of uh, R cube. Let us take these standard. My writing is getting all the more spoiled. Standard basis of R cube. So I'll now write it in a better way. So standard basis of R cube, and let us take what should I say? Let us take some vectors. Okay, and so I'll ease this problem. Okay, so and take some vectors in R square. Take some. I'll not write 3-dimensional. I'll write 2-dimensionally. Let us say take some vectors in R square, and let us say these vectors are say 1 comma 2, 2 comma 3, and let's say 3 comma 4. So these are vectors in R square. These are the standard basis vectors of R cube. And let us define, let us try to obtain a linear transformation concerning or connecting the basis to vectors. And let us say whether this image is unique one or not. So I'm going to put basis here, and here I'm going to seek the vectors. Okay, are you getting my point? So what I want to prove is that what I want to convey is that, see, corresponding to a basis in U, there is only one and one transformation which relates both of them. So here I wrote it for Rn to Rn. So basically here uh, on both sides you had an n dimensional space, so I'll written T from u comma v. So there is only one and one transformation, that is there is only a unique linear transformation, okay, which relates bases to vectors. So here I'm going to show it using one example. I've taken an example of standard basis vectors. Uh, so what I'm going to do is I've taken three basis vectors of R cube, that is 1 comma 0 comma 0 and 0 comma 1 comma 0, and the other one is 0 comma 0 comma 0, 0 comma 0 comma 1. These are the standard bases of R cube, and I've taken some vectors in R square, that is 1 comma 2, 2 comma 3 and 3 comma 4. My intent is to show you that there exists only unique linear transformation which connects the bases in R cube to the vectors in R square. Okay, indeed, you know that if these are the standard bases, then any x, like if I want to write x is equal to x1, x2, x3, I can write it as x1 e1 plus x2 e2 plus x3 e3, right? If I want to write any vector, I can write it in linear combination of the standard basis vector, right? Is that clear? So if I want to take tx, what it will yield me? It will yield me x1 te1 plus x2 te2 and x3 te3. Is that clear? And what is e1? E1 is, I think, 1 comma 0 comma 0. E2 is 0 comma 1 comma 0 comma 1 comma 0, and E3 is what? E3 is 0 comma 0 comma 1. Okay, so if I want to write any vector x in R cube, so I've written if I want to write any vector x, okay, and another thing is, let us, what should I do? Let me first define it, right? Let me first define it. Okay, sorry. Okay, sorry. Okay, let me first formulate all these things. Actually, otherwise you will not be able to get it. So let me first formulate it. So what I have done till now, what I wanted to prove was, so I'll have to develop some mapping. Otherwise, you will not be able to get it. Okay, just give me a minute. Just give me a minute. See what I'll do. I have to first connect it, no? So I have to first connect it. Okay. So let me connect it first. Okay. Okay. So okay. So what is the connection? See, understand again. I'm reiterating. So if you have a basis in U, and if you have vectors in V, then there is only one and one transformation that connects bases to this. So let me write this thing. Okay. So now we want to obtain a linear transformation, and that will happen to be a unique linear transformation uh, from R cube to R square. This is what we want to do, and let us say that TE1 is equal to what? 1 comma 2. TE2 is equal to what? TE2 is, let's say, 2 comma 3, and TE3 is equal to what? It is equal to 3 comma 4. Okay, so this is what I am writing. Okay, now okay, now if I take any x belongs to R cube, what I'm going to get, I can write this as x1, x2, x3. I think this is fine. I can write this x1 in terms of standard basis, that is x1 uh, e1 x2 e2 plus x3 e3. Whether I write this or whether I write this, this is one and the same thing, isn't it? Okay, so if I take the transform like this way, what I'm going to get, I'm going to apply the linear transformation on both sides. This function, this I'm going to get this, then I'm going to get this TE2, and then this is x3, and then you have TE3. Okay, and what am I going to get out of this? So I know that my TE1 I have declared it to be equals to x1 plus 2 x2. I should write, see what is T even. T even is 1, so I'll get x1 into 1 comma 2, then plus x2 into 2 comma 3 plus x3 times 3 comma 4. Okay, and if it, eventually I can write it as x1 plus 2x2 plus 3x3. From here I can get, I think, 2x1 plus 3x2 plus 4x3. Okay, so this linear transformation T would connect your bases in R cube to R square, and this happens to be unique. This is a unique linear transformation that we'll get. There's only one and one transformation that would connect your bases to, what? That would connect your bases to vectors in R square. So let us check it. So if I just take 1 comma 0 comma 0, what I'm going to get? I'm going to get 1 comma 2, and this was it. I told you T even was equal to what? 1 comma 2. So this is a unique linear transformation. This is only one and only one. This is a unique linear transformation that could connect any vector in R square. Here R square is another vector space. So if you have vector space U and V, connecting these two, connecting these two in a manner that you take basis from here and vectors here, there would be a unique transformation. There would be there would be only a unique linear transformation. There is only going to be one and only one transformation. So this is one and only one transformation that connects standard bases in T to the elements in R square. So this is one of the okay. So okay, this is how uh, uh, I can now let me move to some of the vector spaces that are related to. Let us move to the sum of the vector spaces. Some of the vector spaces that are related to a linear operator, and two of them I'm going to pay focus on. The first one is called as a range space. The other one is called as the kernel, and we are going to see it is also called as a null space. Okay, so one is called as a range space, another one is called as a null space. Okay, I'll stick to the word called as kernel first, and then I'll do it. Okay, so let us first stick to the range. What is range? Okay, what is range? So let's say if you have a linear transformation T, so let us define a linear transformation T from U to V. Let us define T, a linear transformation from U to V. The range of T, which I denoted by R of T, is nothing, is the set of the images. I'll write it in mathematics way, is the set where you'll have the images of U. So you'll take all the elements from U, and you are going to see what is the image set that is created. So this is the, you can say, image set of U. Okay, so this is the image set of U. So image set of U is nothing but it is called as a range of T, and this particular space is called as a range space. This particular space is called as the range space. Okay, another space is called as kernel, or sometimes it is referred to as null space. As the word suggests, what is null? Null means for what elements of X the linear transformation is going to be 0. So linear spaces means which follow the vector spaces rule. Linear spaces, yes. So linear spaces is one which follow the linear transformation rules. Yes, indeed. So these spaces happen to be themselves linear transform. Themselves are what you can say. Yeah, you can say that these are the spaces associated with linear transformation. Okay, so I'll write it this way also. So these are the spaces associated with these are the spaces associated with the linear transformation. The spaces are range space and kernel. Okay, and what is kernel? Kernel is called as a null space. And what is a null space? Understand, null space is, in null space we'll consider only those elements for which your linear transformation becomes 0. So I'll write it here very formally. What should I write? The kernel. Okay, the kernel, or I can say or null space, if you want to refer it to null space of T, and we denote it by kernel T. Kernel T is the set is the set is the set of all those elements in U such that Tx is equal to 0. Tx is equal to 0. Okay, and understand this null space is going to be a subset of U, obviously. That is, the kernel of T is going to be a subset of U, and this range will be a subset of V, obviously. Okay, now let us identify a few of them, and then you'll be able to understand. Let us try to identify a few of them, and then you'll be able to understand. So let us take the first example that we took in the, I think, linear transformation, that was identity transformation. Let us take the first example, which is the identity transformation. So let us define an identity transformation from V to V such that I of V is simply equals to V, right? I of V is simply equals to what? V. So this is how you define your identity. Okay, we want to find what is the range of I. So range of I will be equals to what? Range of I will be simply I of V for all V belongs to V, and which will be equals to nothing, but it is equal to V for all V belongs to V. So we can say that range of I would be complete V only. And what do you think the kernel of I would be? So kernel of I would be, kernel is what? Kernel is, we want to find all those elements in V, because here it is transformation from V to V such that the IV becomes 0. And if IV becomes 0, it implies what? It refers to all those V belongs to V such that V is equal to 0, and is equals to 0. 0 is, understand, this 0 is identity element. Sorry, this is additive identity. This is additive identity in V. Okay, this 0 is what? This is additive identity in V. It is not always single 0. Okay, understand. Additive identity in V. So this is additive identity in V. Are you getting my point? So this 0 is not exactly 0, means, say, let's say R square, then this will be 0, 0. Let us say this is a set of matrices V, then it would be 0, 0, 0, 0. Okay, so let's say if it is, I'm referring to this, then this 0 would refer to what? 0, 0, 0, and 0. So don't confuse it by 0. It's a vector 0. Okay, so just do one question for me, and just want you to know this thing, nothing good about it, and just want to help you with the theorem which is called as a rank nullity theorem, because that is it. You as a physicist, you should know that there is a rank nullity theorem, and how the rank and nullity are related to each other. This is how you should know. Okay, so this is, so today I'm going to just discuss this only, how to find kernel and range. So let us take another example in order to understand this. So let t be defined from r cube to r square, such that t x1 comma x2 comma x3 is related as 3x1 plus x2 plus 2x3. Okay, and we want to find the range of t, and we also want to find the kernel of t. We want to find the range of t, and we also want to find the kernel of t. So see, range of t would be what? Understand a few things that I want to uh, make you understand. Okay, let us understand a few of the things. So not r square. This is r. This is r. See, I've added them up. So basically, what I'm getting a single element here. So I'm getting a single element means this is r. This is not r square. Okay, understand the point that what is range of t? So first thing is, what is range of t? So range of t would be equal to x1, x2, x3. Let's say all of them belong to r, with the condition 3x1 plus x2 plus 2x3. So what we want to see that what will be the values attained by x, which is equal to 3x1 plus x2 plus 2x3. So if I take different values of x1, x2, x3, what would be the value attained by this? So don't you think that this will be, since x1 comes from r, x2 comes from r, and x3 comes from r, 2 times r is again r, this is also r, this is also r. Don't you think that the range would be the entire real number line? Okay, because you see, understand, you will take x1 from all real r, you will take x2 from all real r, you will take x3 from all real r. If you're going to do that, uh, after all, you're going to get the complete, you can say, real number line, isn't it? Okay, let us take an example. So let's say alpha belongs to r, be any arbitrary element. I'll take any arbitrary element. Any arbitrary element means what? Any alpha belongs to r. And let us try to take the image of t of alpha comma 3 comma 0 comma 0. It will come out as alpha. Alpha belongs to what? Complete r. So your linear transformation will the range will contain all real r. The range will contain all real r. And what would be the kernel like? What do you think the kernel would be? So kernel of t would contain all those points x1, x2, x3, such that 3x1 plus x2 plus 2x3 equals to 0. So we'll only have the points where 3x1 plus x2 plus x3 is equal to 0. What do you think this is? Don't you think that this is a plane? So if you remember your three-dimensional geometry, if I divide it by 6, let's say this is x1, let's say this is x2, and let's say this is x3. So this will only contain all those points which lie on the plane. Which lie on the plane. So the kernel will contain only those points which are lying on this plane. Is that clear or not clear? Please let me know. If that is not clear, please let me know. See, kernel is what? Kernel is all those elements x1, x2, x3, such that your 3x1 plus x2 plus 2x3 becomes 0. And if I'm saying that 3x1 plus x2 plus 2x3 is becoming 0, understand that this is an equation to plane. And so this kernel of T would be nothing but it will be equal to the plane in R cube. So it is a plane in R cube. So all these points are going to be the are going to use, you can say, uh, form what is called as the kernel of T. I hope it is clear. So there are a few other people other than Bharat also. Please let me know who all are there right now, and is that understandable or not? Okay, so nobody is right now. Is that clear or not? Or is that too difficult for you to understand? Please let me know. Otherwise, see, just understand all these things. They are not required as such. I'm just giving you the definition so that if in case I use them somewhere, so that you will be able to just keep them in mind. That is what I want to say. Okay, so these are called as kernel, and so these are just some special names. Okay, now I'll do one more question and then we'll do another topic. Okay, so in okay, and also understand. So now let us again go back to things. So I initially told you that these are the vector spaces which are related to linear transformation. So indeed, what is range space? Eventually, you understand that range space would be what. So let's say if I'm defining. So if I'm defining a linear transformation T from U to V, the range space would be subset of V, right? After all, whatever range is there, it is going to be a subset of V, right? So I'm writing the range of T would be a subset of V, and kernel of T would be a subset of U. And it can be shown that, and I'm not going to show right now, but it can be shown that they themselves form a vector space, or you can say that they are subspaces. They are not only subsets, but they are subspaces. So these are some very peculiar vector spaces which are related to the linear transformation. Yeah, we'll have another examples to understand. Just understand means like in physics, you're not going. It's not that required, but just understand that these are some definitions, because probably when I'm going to go further and do eigenvalues and eigenvectors, and then there are cases where I'll use these terminologies. So just have an idea of all these things. Just have an idea of all these things. Okay, a few more examples to illustrate rank and sorry, not rank, sorry, range and nullity. So range and kernel, sorry, not rank and nullity की जगह बोलना है range and kernel. We have to say range and kernel. Okay, we want to see what are range and kernel. I'll come to rank and nullity also. They are nothing but they are dimensions of the same. So if I want to say what is the dimension of range set and what is the dimension of the kernel set, then I'm going to talk of something called as the rank and nullity. And there is a very celebrated theorem of linear algebra which is called as, I think, Sylvester's theorem of nullity, or otherwise the rank nullity theorem. So okay, till that portion I'm going to cover today. Okay, so okay, so let us take some examples. Okay, let us take examples of projections. So initially I taught you some projections. That is, if I want to project my uh, three-dimensional vector onto a plane, if I want to project my three-dimensional vector onto a plane or onto a line, then I'll use a linear transformation. And I've proven that these are linear transformations in general. So understand that projections are linear transformations. Okay, and indeed we also did some projection over some specific coordinate, that is J, and we wanted to see that whether it forms a linear transformation. Yes, it does form a linear transformation. So we are going to discuss some projections. Let us say I want to project a three-dimensional thing to a two-dimensional space, and let's say it is related with this kind of linear transformation, and I know that I'm not going to prove that this is a linear transformation. Indeed it is. So let us try to find what will be the range of t. Let us try to find what would be the range of t and what would be the kernel of t. What would be the kernel of t? So we want to find what would be the range of t, and we also want to find what would be the kernel of t. Okay, so again, so what would be the range of t? So range of t would, what should I say? The range of t is what? After all, we want to find, if I place x, y, z, where it is going to get mapped. So it is going to get mapped to x and y only. So if I take x belongs to R, if I take y belongs to R, so after all, it will be element in R square only. And if I can take all x and y, if I take all x belongs to R and all y belongs to R, so it will, so what would be the range of t? So I can say that if I take any arbitrary point from three dimensions, and if I relate it using this, if I relate it using this transformation, that is t x y z equals to x comma y, so my range of t will be nothing but it will be the entire plane. It would be entire plane. So this is entire xy plane. Entire xy plane. So complete R square. Complete R square. So this is my range. Complete R square. So my range of this transformation would be the complete two-dimensional Cartesian plane. It would be a complete two-dimensional Cartesian plane. Okay, and what would be the what do you think the kernel would be? So kernel would be simply the coordinate that is origin. See, so according to the definition, what is kernel? Kernel T refers to all those elements such that it becomes 0. And see, this is not 0. Understand, this is 0 in what? This is 0 in R square, because this is a transformation T from R cube to R, na? So this 0 would be what? 0 comma 0. So this refers to x comma y becoming 0 comma 0. So in kernel, you will have the origin coordinates, the coordinates of origin. No, the kernel would contain 0 comma 0 and see what I want to say. This would be my mistake. See, this would be in R cube, right? See, understand again. Sorry, my mistake, my bad. See, understand. So x and y would be 0. If x and y are 0, see, kernel is what? Let us say I'm talking of a projection from R cube to R square. Okay, kernel consists, I'll write in English so that you'll understand. Kernel would consist of elements This is right. This is right. Kernel consists of elements in R cube for which t x comma y comma z becomes 0, where 0 is in R square. That is absolutely fine. So from here you will get that x becomes 0 and y becomes 0. But you don't get an information about z. So z can belong to any real R. So kernel would consist of, so this would be your kernel. Kernel after all is a subset of R cube, and range is the subset of R square, understand? So my kernel would be 0 comma 0 comma z. Okay, it will not be origin, sorry. It will not be origin. This is fine. You have to compare x and y to 0 comma 0. That is absolutely fine. So here you'll get x equal to 0 and y equal to 0. But understand, we are not writing in R square. We have to write in R cube, because kernel is what? Kernel is in the domain set. So domain set is what? R cube. Okay, sorry. So the kernel would contain 0 comma 0 comma z. So not origin, rather it will be simply z axis. Is that clear? Or not clear? So for example, I'm again drawing a diagram. Let's say this is my three-dimensional space, which is R cube, and this is my two-dimensional space. Okay, this is my two-dimensional space. And if I'm relating any point x, y, z via transformation projection, that is tx comma y comma z is equal to x comma y, the range will form the entire Cartesian plane. The range will form the entire Cartesian plane. This is the range. Is that clear? This is my range. So this is my range, the entire Cartesian plane. So range of T would be entire Cartesian plane. What would be the kernel? Kernel would contain only one point. Kernel would contain only this line, that is the entire z-axis. So this is my Is that clear? I hope it is clear. I hope you've not got confused. Actually, while writing, I made a mistake. So basically, this is fine. This is fine that if I want to write tx comma y comma z, it would be 0, and 0 would belong to R square. Indeed. So from here, you will get that x and y both are 0, but you cannot say anything about z. So z will belong to all real R. Z can belong to all real R. So why you take x and y to be 0? Okay. So see. Now again, I'm coming back to the point. See, what is kernel? Understand my mistake here. Why? Actually, I got confused. So what is kernel? Kernel will contain, I'm writing it in English so that you'll understand. Kernel will contain all elements. So if I have a linear transformation from U to V, all elements in U such that TU becomes 0. And this 0 will be contained in V. So if this is V, okay. Now you see, if I'm saying that I have a projection defined from R cube to R square such that if I take a three-dimensional vector here, I'll get a two-dimension here. I want to find what is kernel of T. So what is kernel of T? Kernel of T would be all those x, y, z such that it becomes 0. 0 means what? 0, comma 0. Is that clear? Okay. And what is tx comma y comma z? This is nothing but it is equals to x comma y. So x comma y becomes 0 comma 0. That implies x should be equal to 0 and y should be equal to 0. So kernel is what? Kernel is a subset of, I'll write, is a subset of R cube, sorry. It is a subset of R cube. It is in domain. I want to find what are the points in the domain which I place in the transformation T such that I get a 0. 0 in what? 0 in V. Which is here what? Which is here R. Here you have this R square is V and R cube is U. So kernel is a subset of R cube such that X becomes 0 and Y becomes 0 and nothing about Z. So Z is all real R. So the kernel would contain all these elements, and this is what? This is not origin, rather it is the entire Z axis. So your entire z-axis would be your kernel. Is that clear? An entire plane, that is entire Cartesian plane R square, would be your range. Is that clear? And it can be proven, I'm not going to prove this now, it can be proven that this range space and this kernel space, okay, like these are two subsets. These are not only two subsets, rather they are subspaces. Okay, so this can be proven. I mean, this is an easy thing to prove. You can do it on your own also. Like the basic definition of subspaces, if you put into perspective here, you can easily prove that this null space and the range space, they themselves are vector spaces. That is why we'll say them as null spaces and vector spaces. So these are the linear vector spaces which are associated to the linear transformation. So you can say these are the vector spaces which are associated to the linear transformations. Are you getting my point? Now, having said all these things, there are two important things that I'm going to write, and I'm going to conclude it here itself. The two important things are called as rank and nullity. What is rank and what is nullity? So right now I'm going to only discuss for the finite dimensional cases. So consider, what should I say? Consider a linear transformation defined from U to V such that the dimension of U is finite. Such that the dimension of U is finite. And we already know that the kernel of T is nothing but it is a, I have already said that it will form a subspace of V, subspace of U. Since it forms a subspace, so obviously the dimension of kernel of T would be at least less than or equal to the dimension of U. And what is range of T? Range of T is nothing but it is equal to the images of U. It is nothing but it is equal to the image of U. It is equal to the image of U. Okay, and it so happens that if dimension of U is finite, if dimension of U is finite, then obviously the dimension of range space, let's say it is equal to n, would be less than equal to n. I'm not going to write all these, I'm not going to prove all these things, just understand. Just understand. The dimension of range space would also be finite. And having said all these things, there are two terms that are important. So what is dimension of range space is known by a special word called as the rank of T. Okay, and or you can say the dimension of null space, or you can say the kernel T is known by a special name called as the nullity. Okay, this is called as the nullity. This is called as the nullity of T. Yeah, in general nullity. So nullity is nothing but it is the dimension of kernel T, and rank of T is nothing but it is the dimension of the, what you can say, dimension of this. And one of the most powerful theorem, one of the most powerful theorems in linear algebra is called as the rank nullity theorem, and which is related this way. I'm just writing it and I'll start things from here tomorrow. And I think this, we are coming to the end of this, and probably one more topic called as a dual space that we need to see, because see why we need to concentrate on dual spaces. See, whenever we study in quantum mechanics, we have this we say that this is our row vector, and then there is a corresponding bra vector also. So corresponding to every row vector there is a bra vector. Okay, so corresponding to every row there is a bra, and this is an element in the dual space. So we need to understand what is a dual space. That is why all these things I'm writing now, so that at least somehow you just fix them in your mind. Don't go and start reading linear algebra, because see, understand linear algebra for mathematicians are a 2-semester course. So whatever we are doing right now, I'm just skimming it, like probably in 9 to 10 lectures I'll skim entire thing. But understand, this is something a mathematician studies for almost 2 semesters, not even 1, 2. So if you go till unitary transformations and probably till the topic of Jordan canonical forms, this comes entirely in the MSc syllabus. Okay, so a person in mathematics will study entirely whatever you are studying right now in BSc and then in MSc. So this is that long a course. So it will take eventually almost an year to complete. If I go on writing each and every theorem and derive each and every theorem, I am here to just actually write all those theorems or all those things that you can relate with physics. So whenever those things come in physics, you can relate back them to your linear algebra thing. So I will only advise you that whatever I'm writing right now, just write down in some copy. When I'm going to do some questions, so the appropriate questions, just note down according along with them. So for example, if I'm doing questions with linear transformation, note down them with linear transformation, so that whenever you're going to study linear operators in quantum mechanics, you can relate them. Let's say we are going to study matrices of linear transformation. So then you can relate it with the matrices that you form in the angular momentum, the matrices that you form in the spin. So basically, there is a topic called as a matrix representation of operators. Okay, so then this particular thing, that matrices of linear transformation and matrix representation in quantum mechanics, they're going to get aligned. So that is why I'm creating this kind of structure before getting into quantum mechanics. Okay, so this is my general advice that I've given to you. And let me write a beautiful theorem which is called as let U and V, and we'll focus on all these things tomorrow, be the vector spaces, over a field F, and dimension of U is simply n. Dimension of U is simply n, and let us define a linear transformation linear transformation T from U to V, or you can say in physics you will say it as a linear operator. Then always remember that the rank of T and the nullity of T is equals to, if I sum them up, it is equals to n. This is an important theorem in linear algebra. From here we are going to continue tomorrow. I hope you are able to get the gist of all those things. That is the linear transformation. Probably tomorrow we are going to see the dual space also, and then we are going to revisit the theory of matrices all over again. And the most important part of matrices that we want to see is called as the matrix of the linear transformation, where our all concentration should be focused on. Okay, so I hope to meet you tomorrow. As I told you initially also, I'll keep telling it time and again that please keep patience with all these things. Try to understand all these things. If you're not able to understand the derivation part, fine. That is like, if you're not able to understand the proof part, then also it is clear. You can simply write down the statements. See, to write a proof, it's a mathematics business. Okay, so basically, being from mathematics background myself, I don't like anything to be written like this, that this is a statement, just remember this. But for a physicist, the challenges are too many. Now, if he is going to even write the proofs for mathematics, then how is he going to complete his course on quantum mechanics? Okay, for example, our own course in quantum mechanics is a 2-semester course. If you go till scattering, it is not even covered in 1 semester, it is covered in 2 semesters, and I have to cover it in 1.5 months. Okay, so somehow we have to skip a few things. Okay, so I hope to meet you tomorrow. Till then, take care. Bye bye.